Welcome back everybody to the last day of the first week of the workshop, and it's a pleasure to introduce Riccardo Gonzo from Queen Mary University of London, who's going to tell us about self-force and critical objects.
Thank you very much. Well, first thanks to the organizer for the invitation for me to get such a nice workshop. I think it's really perfect, because well, holography puts together particle physics in gravity, right? And I try to go in a slightly different direction, more of what Carlo has been talk about, gravitational waveforms, but still it's deeply connected with holography, and I try to make some connections along the way. So yeah, I'm going to talk about basically trying to get an effective field theory for the gravitational self-force problem. Okay, so one of the biggest discovery, in history of physics, in the past century, has been the gravitational waves. And this really, this event that was detected in September 2015, really, confirmed Einstein gravity, but not only in the weak field regime, but also in the strong field regime. That's really given us a new window to see the universe and to learn about black holes, compact objects that are in the sky. So these are two big compact objects that are very far away, right? Also very far in time, actually, because by the time they detect a signal, it's traveled to us. So they come together into this paraphase, they merge, that's where the signal is the biggest, in the strong nonlinear regime of gravity, and then they finally set in this rip-down phase. Right now, we're really entering actually the precision era. So, we got discovery a little bit more than 10 years ago, and now you see this nice collection of events. So we have almost 400 events detected by the LIGO collaboration, so a set of detectors, ground-based detectors. This line is going to increase and go up. Not only, these are the current detectors that we have, but we will have many more in the future. So I think I need some presentation mode.
Control L.
I think it is Control L.
No.
Oh, yeah, now it's perfect. Okay, thank you. Yeah, sorry, bear with me for a second. So, there will be both upgrades in current detector selectivity, but also new ones, and which I'm very excited about. So, the first one that was approved last year is LISA, Large Interferometer Space Antenna. It's a space-based one, and we'll also operate at different frequencies, and it's particularly exciting. I will also tell you later why. The Einstein Cosmic Explorer, which are the advanced stage of planning, and all these things, in roughly 10 years, they will be online. They will detect many more events, and really this to get the most out of this, we need to understand if you're really ready as a theoretical physicist, can we model this system, right? Are we ready for what lies ahead? And this is one of the questions that drives me into this. Way of thinking about gravity and particle physics. I'll let you why now particle physics is important and how it's connected. So in general, when you get these signals, there's really a lot of noise, okay? And to detect the signal, we really need to do some filter, okay? To get some filter, to get some small signal out of the noise. And it's not possible today just to extract the signal unless we have a theoretical model. And to get a theoretical model, you need a theoretical model of the binary dynamics, okay? Because these are compact objects, and you need to know how they evolve under the Einstein equation. So this is very important for a set of phenomenological questions that I think it's worth pointing out for the connections. One is for cosmology, okay? So we can try to test for example the Hubble constant, okay? That's something that I'm very excited about because, as you know, there's been some tension, and this will be an important test in the future once we have enough events. Black hole astrophysics, so the cosmic universe, how the population of black holes form, what's their evolution. Not only black holes, also neutron stars. We can test strong field the universal equation of state, so like an exotic state of matter, right? So which is also important, like because we think about QCD and what are the regimes that we don't understand about QCD, right? So that's also something about strong QFT type of questions, and of course test Einstein gravity. So detect deviation from GR. So far we kind of probe gravity mostly in the weak field regime, right? So testing gravity in the strong field regime is really something completely new. And in general, I think gravitational waves provide some fingerprints like of the sources and also gravity itself. So, and the only way to resolve this is you really think, at least from theoretical perspective, is really solving Einstein equation, because we know it's the most accurate description of gravity so far, and this can be done in various ways. So it can be done on a computer. You can use numerical relativity, okay? But this is kind of slow. You have to run these big simulations like that, discretized spacetime, it takes really a long time, to do. And for each parameter, you have to rerun the simulations. Or, if we like perturbation theory, any kind of perturbation theory, we just expand. So that's what I like. So this is kind of a fast way, if you want. So here you can see a plot, a cube, like to call, with all these different expansions. So you can see, so on the x-axis you have the separations, okay? So separation when the bodies are far apart, clearly it's in a weak field. So you can try to use post-Minkowski and post-Newtonian too, which I'm going to talk about. Or you have eccentricity. So most of the events to be detected are circular orbit binaries, but in general, in the future, we are going to detect something much more complicated sources. And particularly, we might be able to detect also hyperbolic encounters, kind of scattering events. Okay, and scattering events are very closely related to quantum field theory, which is why I'm also interested in trying to understand this connection. On this z-axis, we have the mass ratio. So far, most of the events are equal mass binaries. Okay, but in the future, especially with this LISA, the type of frequency sensitivity of LISA, like when it will be in the space, will be able to detect the extreme mass ratio binary events. So why I like this kind of thinking about asymmetric mass ratio binaries is that right now the type of signals that we detect are kind of few oscillations, okay, 10 to 100 oscillations type of events. So right now, the codes on the computer on the numerical side are doing quite well. They're still slow, and to populate the parameter space to get the mass and the spin is very hard. But they can kind of do it because it's 10 to 100 orbits. In the future, the thing is that the number of oscillations scales something like the inverse of the mass ratio. So if the mass ratio is very small, so you have some big supermassive black hole and some small black hole, the number of oscillations will be much, much higher, and we can really not use numerical relativity. So basically, right now still there is need for analytical tools, but in the future will be more, much more. So it's something that it's coming because, as I said, LISA was approved. Other the propagation sensitivity in the current detectors are also going to help this, in collecting more events. And I think this is really something very important. So, okay, so let me walk through this kind of perturbative scheme. So, as I said, numerical activities is.
Can I just out of curiosity? So you said also hyperbolic encounters could be. Is there some study about?
Yeah. So there is a paper about studying a current dynamical capture event in terms of hyperbolic encounters. The waveform that Carlo was talking about right now, for hyperbolic encounters, basically just a jump. And so there is some kind of event like that that's been studied and identified as an hyperbolic encounter. It wasn't still sure, but I heard from Davide that now they are realizing the data. They are very sure that it's an hyperbolic encounter.
And so it's already there.
It's already there.
It's not that it's already there. It's all the data analysis that they did is pointing to the fact that it is a dynamical capture. So
But this is the all. I mean, is
Yeah, it's a few
It's that
years
one,
ago,
yeah.
but they redo the analysis,
I see.
constraining even
Is the one
better
that Alessandro Nagar
yes,
studied?
yes,
Yes,
that one.
yes.
And now it's a kind of more
There is
convincing evidence that is a capture.
Yes, yes, yes.
So in the future, hopefully we're going to take much more of that. So even that, like, brings new questions. So, okay, so as I said, the numerical activity is kind of sits here because it cannot do like a symmetric, okay, mass ratio. It's quite good for what we see right now, but in the future won't be enough. It can also not do very large separation, which is, traditionally very large separation is actually more scattering kind of thing. It can also be like, when it's here for the bound, you really mean like some expansion. So, the oldest type of expansion around Newton is called post-Newtonian, okay? So after Newton, and just expand like in slow velocity. Not sure why. Yeah. So it expands like in a slow velocity, okay? And that's a very natural expansion. And then the kind of breakthrough like in the game has been like studying like scatter events or very eccentric events, right? Because these events like are very naturally captured by particle physics, okay? If you think about particle physics, you think about S matrix, and S matrix is scattering, okay? Of course, you can study bound states with S matrix, but it's more complicated. And so this is actually something that happened quite recently. So compare these dates indicate like where more or less the breakthrough. So this is the discovery of Pretorius, like on the how to do like numerical relativity 20 years ago. I would say around 2000 there's been some breakthrough like in the gravitational cell force. MST formalism, for example, we have discussed, right? Post-Newtonian started much earlier. It has to keep pushing, so it's getting much better. We need even more, so supported to post-Newtonian, keep doing. But the point is that, just after the discovery of gravitational waves, like this has really been the breakthrough and has really changed also the way that I think we think about the problem as a theoretical physicist. So anyway, so the point that I want to say is that you see that these perturbative calculations, they all overlap, right, in this group. So they're not separated. They overlap with each other. And this is useful as a cross-check, but also as a way to use synergies, to kind of put together these kind of things. So this is, I think, something very important in the future, like that we really try to put together like all these different techniques to cover the parameter space for the future for the gravitational wave modeling, but also, as a kind of, I would say, as a way to kind of put together also the communities, right? Because the GR community is being separated by the particle physics one, but I think it shouldn't be that anymore. So, and the question I want to ask is, what can particle theory teach us about these questions? So I'm going to talk about the cell force expansion. So that's here, okay? So I'm going to start with the simplest case, which is like a geodesic, for example, in pure spacetime. So it's clear that if you set the mass ratio to 0, one mass is much bigger than the other, and you recover the case that you have just a probe particle in a background, okay? So for this case, so what I'm going to use as a model, but you can take your favorite model. You can use like pure amplitude tools, like was discussed by Carlo and others. But I won't talk about the Worley formalism because it's very natural in this kind of expansion. So one way of describing these black holes, for example, using like an n equal 2 SUSY model, at least up to spin square, where like the spin tensor is just a product of these fermionic degrees of freedom. And this is in the first order form, so it's, I don't know, p mu x dot mu. I'll use later the second order form. You see here that you have some constraints in the first order form. So one of them is just on shell, so the on shell asymptotic constraint, being on shell, and some other self-conservation of some SUSY charges and the U1 charge. So this is just a model, right? So, but this is actually reproducing the physical spin in black holes, and that's why I want to use it. I'll say more about that later. So I'll start with the simplest case. So I was talking about geodesic case. So I just think about the radial action. So radial action is the analog of the Icona, right? So we discussed a lot about Icona, I think, this week. You can think about an angle of that because it's very, at least in the problem, they're essentially equivalent. And the idea is to, when you have this particle moving in the background, you take the radial momentum, okay? The problem is integrable, okay? So the problem is integrable, so you have to think about basically conservation of angular momentum, fix like my p phi component, okay? Conservation of energy, fix pt, so you are left over with something non-trivial that is just the radial momentum. And for scattering, then I'll do scattering, but much of what I say applies also for bound. You reintegrate like from the turning point to infinity, and also there's a factor of 2 missing, but okay, because it integrates from the infinity to the turning point and back. Right. So in this case, like the interesting part about this problem is that it's an interesting problem because it's classically integrable, so you take the on-shell constraint. So this is the one that was here, over here. Okay, the Hamiltonian on-shell constraint. And you try to solve it for it because you have this conservation law, energy, angular momentum, and also, crucially, Carter constant. So the conservation related to basically killing tensor symmetries. All the conservation of energy and momentum are related to killing vectors. This is a killing tensor symmetry. So you can solve for PR, and this will give you a solution because the problem is separable. So that you have an expression, okay, and you can integrate this expression. And that's all you need to understand geodesic motion. That's all you need. Once you have this radial action, you can compute anything else. All the other observables. And this also provides like kind of a gauge invariant complete perspective, like on at least a geodesic order on the program. So once you do the integration, you get something that looks like complicated. This is not, there are different formulas. So if you're really smart, you can reduce this to some sum of elliptic functions. So I'm not, so I'll just use simple like hypergeometric definition. So you can just, if you have an integral, like you think about the integral here, like from PR, you're gonna have like some square root of potential. So you factorize the potential in terms of roots, right? You have 4 roots for care. And then you can just integrate in terms of some complicated hypergeometric function. The point is explicit, and this is like a strong, varying the strong field as well, not only in the weak field. And this is going to be crucial for what I'm going to talk about now. So if you look for structures, you try to simplify this. You can take the master's limit, you can do it. Okay. So this is just null geodesic in care. So then from some complicated FD4 function, like you just reduce to some less complicated function, which are still complicated, some ARG function and some 3F2 function. And you see that their argument is interesting. Now you have like less scales in the problem because you just throw away the mass. So you just one less scale. And the Euclidean scale is only just this x, which is the ratio of the angular momentum to the critical angular momentum. So the critical angular momentum is the value for which you shoot a particle, okay, you have a black hole, and at some point, like if the angular momentum is too small, the particle just plunges into the black hole, okay? The interesting thing is, of course, it's also proportional to Gm, so it's a non-perturbative effect. From the point of view of the weak field expansion, you don't see it. If you expand these functions, you don't see this branch cut in this particular structure. So it's very interesting that how it arises here. And in some sense, like this is a smoking signature also the strong field physics, right? So exactly like looking at how this kind of transition between scattering and plunge regimes in separatrice, how it is called. So this has been, for example, also studied by Andrei and Carlo, like from the ADS perspective. So they studied the Icona phase in ADS, they take the flat space limit, and they made this connection also with this critical angular momentum. And I think this is very interesting for a series of applications we're going to talk about here. And I just want to make the point that if you're able to to get a very close form expression that's very nice, you can just connect analytic structure of strong field physics and compute it, because here it's classical physics, so it's something you can do. So if you use Hamiltonian Jacobi theory from this, you can just start the deflection angle. Again, you get some expression. That's the same branch cut, okay? And you see that if you expand around the branch cut, you start to get like some, in this expansion of L that goes to, basically the critical variable momentum plus a small perturbation, okay? You get a log of this delta L. So this is quite interesting because, it diverges as delta L goes to 0, just this blows up, okay? And the fact that it blows up, it's something. If you do this thing numerically, right? It means like that, the value is going to be very large around this value of the critical angular momentum. And so in particular, the weak field expansion I was talking about, like the post-Newtonian, post-Minkowskian, are not very good at capturing this kind of effects because this one just blow up around this region. But what you can do is you can try to think about how to understand this thing analytically, like I've done here, and try to extrapolate this idea to other contexts to do resummation. So the reason why this happens from the physical perspective, okay, if you consider scattering orbits, is that these are plot, like basically it's a Schwarzschild geodesics, okay? And you have like their energy on the y-axis, and basically 1 over the inverse of the distance, okay? This is very nice because it becomes a compact region. So basically, if you do this, because it's 1 over, so it becomes a compact region. So you see these orbits here are Zumwil orbits, where basically the particle comes very close to the black hole, okay, wraps around an infinite amount of times, a logarithmic infinite amount of time, and then it comes back, okay? And this is at the boundary of the region. So it's clearly a good idea to study the boundary of the region of this space, of the parameter space, because it provides insights on the divergences. Let's see if, sorry about that. Okay, so it's clearly a good idea to study this because if you have control of some weak field expansion in some region of your parameter space, if you have control of what happens at the boundary, you can use that for doing some resummations. Okay. And the interesting thing is that this not only applies for scattering but also bound orbits. So actually this curve goes smoothly into the bound regime. So you can use it in the same exact way. And indeed, if you compute like the periastral advance, which is the analog of the scattering angle, which is basically like the advance of in the phi coordinate, like on the plane a bound orbit, it also has a similar divergence. So with the same coefficient in this case. Anyway, so the point is that there is first how can you make use of that? So how can you understand that more in detail? And why it is important. Also for the connection for things that I discussed this week, in particular by Manuela.
Sorry?
Yeah.
So this plot is for Schwarzschild?
Yeah.
But before you were talking about CAD black holes?
Yeah.
But so this plot would be different, no?
Yeah, you can study the Kerr separatrix. It's more complicated form, but you can do it, and has been done.
You still have bound, still
Sure, yeah. It's just more complicated. You have one parameter.
Okay.
So but this has been done. Yeah. If you're interested in the papers, I can let you know.
Sorry, maybe another quick question. So the log divergence comes from both terms in the deflection angle? Or?
Yeah, exactly. I'm about to show that. So thanks you for bringing for the next slide. So that's exactly what I'm going to show. So you use geodesic in Schwarzschild, as I told you, is a separable problem, classically integrable. And the separatrix curve is basically determined by this condition. So that it's turning point equation. So r dot is 0, but also r dot is 0 in the radial direction. And so this means that the energy squares the potential, and then the first derivative vanishes, and the second derivative has a certain sign. Okay. So when you study from this equation, you just solve for the angle. So the angle is just the azimuthal component, right? So you just in GR 101 or whatever it's called. And so you integrate over the full trajectory. You change variable from dt to dr. And now you see that this r dot comes at the denominator, right? So this r dot is just written here. So you can try to expand around that point, because now I know that the first derivative vanishes, so I have just a quadratic term for the expansion around the turning point. And once you do this, like you recover exactly this log singularity. So now there is a coefficient because this is the full massive result, not massless, right? So I just simplified before the story with this calculation, but that is now the massive result. So this I think has rich applications. What I'm going to stop about for a bit. So okay, I'll start with one of the oldest one I think, like unstable circular orbits have been connected with quasi-normal modes. This is something very old that has been done, and quasi-normal modes also they connect like with the ring down. I'm not going to talk about that. They are related also this kind of structure to gravitational lensing effects. So you can think that this is actually the recent work. You can think about this, the fact that the previous orbit was wrapping around many times, like the black holes. You get many black hole images, okay, out of that if you shoot a piece of light. And so you can also exploit that for gravitational lensing. You can also think about holography. In particular, this nice relation between bulk null geodesics and boundary correlator structures. There's many people here, so sorry if I don't know anyone, but it's just like, there's some work, for example, by Cristoforo and Robin on this, and also Manuel and Andre, and many others. And this is the SEFT, but this kind of structure maybe also be understood in flat space. And the new idea is trying to use this weak to strong field resonation for observables in self-force expansion. Is that clear so far? Questions?
A trivial one.
Yeah.
Well, in the third point, so the SCFT, which I don't know really well, but from what I understood from the talks in these days, there are different kinds of null geodesics, right? I mean, this is a physical particle. In those cases, you have null geodesics which are not describing any physical. I mean, it's a confusion I have maybe.
The interpretation might be different in ADS because of the particular causal structure of ADS. But I think like the relation between singularities in something that is a boundary correlator and these kind of orbits, I think is more general, right? So it hasn't been studied in the flat space context, but sorry, let me see. I'm not sure. Yeah, okay. Let's see if we move also slide. Yeah, okay. Perfect. Okay. So yeah, it's. I think the relation is more general, but it is true that the causal structure of ADS is slightly different. But I think these are critical points in parameter space when you try to think about these objects, like in terms of energy and momentum, for example. So it's something that in semi-classical approximation can definitely be exported in other contexts. Other questions? Okay. So now, of course, we want to do this surface expansion. Geodesic is done. Okay, so you understood. So we try to go beyond. And you can think about the geodesic solutions arising from the two-body action, like when you take a light body, an heavy body, and a couple of GR. There are three types of pieces. And if you send this parameter to 0, okay, you want to eventually land in this type of action, word line action, which reproduce the geodesic equation, which is just tautology in some sense.
Maybe you're going to say it, or maybe you already said it, but just to. So is this like unstable bound geodesics going to produce some similar singularities in the S matrix?
Yeah.
Okay.
Yeah, definitely in S matrix, because the S matrix you can think, at least in the probe limit, is just like related to some exponential of this radial option,
So
just like the Econa. So then
it's really the same as ABS.
sorry.
Okay, it's the same sort of singularity.
The same, yeah. So it's so you can think about this expansion. So leading order, you recover geodesic equation. The interesting part is going beyond this. The reason is that people doing black hole perturbation theories, they use particular kind of, for example, regularizations that are adapted to 4 dimensions. But as a particle physicist, you like dimensional regularization, for example, because it's gauge invariant. So you don't want to do that. You don't want to go to just 4-dimensional, but stay in D-dimension. And there's this interesting series of papers which developed the spinless version of this self-force EFT. And the main idea behind this is that when you solve the equation of motions, like for the Schwarzschild black hole, is not a vacuum solution, but is generated by one other particle. So in particular, this Einstein equation, then you still keep the delta functions of the heavy body in this equation when you solve it. So when you impose this equation, people usually say Schwarzschild solution is a vacuum solution, but at the source there is a divergence. Okay, so if you go just directly to the source, so it's very natural to think about this metric generated by a point particle, and then to handle divergences on the background metric. The nice discovery is that you can use dimensional regularization. So if you take Schwarzschild metric, you send R to 0, it blows up. Okay, that's a triviality. But the point is that if you do dimensional regularization, the Schwarzschild metric, evaluating on the heavy particle, so I'm talking about the heavy particle when it's evaluated, it just reduces to the flat one, and so it doesn't blow up. You can show this, that dimensional regularization is equivalent to this statement, and this is a super powerful statement that has never been exploited before, and this is what allows to go, beyond the usual ideas of doing black hole perturbation theory in 4 dimensions. So this is absolutely crucial. And indeed, what happens is that in this kind of approximation, the heavy action just reduced to the free action for the heavy body, which is important because it must be free, because the body is just there, it's not doing anything. And so you discover the free trajectory. So I want to do this for spin. So in the spinning case, you can take, so a spinning case is very interesting because there are no uniqueness theorems beyond d equal 4, as Fabio is going to discuss this afternoon. So in particular, there are many extensions of the Kerr metric, and Myers-Berry is a famous one. It's only one of them, okay? And in some sense, it has nothing special except being discovered, and it's the right time with the right symmetries. But it's one of them. You can parameterize in a fancy way. It doesn't matter what it's written here, but you can write a covariant Lucchi parametrization. And the idea is that if you want to cover something like Kerr black hole, usually in this Myers-Berry structure, you have many angular momentum, but you want to take one of them not vanishing, and in such a way that you get smooth Kerr limit. So this is crucial because I'm going to do 2D dimension, right? So I don't want to set up my perturbative scheme beyond 4 dimension. So yeah. As I was saying, this is only one of the infinite deformations of the Kerr metric above 4 dimension. It's interesting because also, as pointed out by Fabio and also his collaborators, that it's not the simplest one. So if you think about minimal coupling in terms of point particles, this is not the simplest solution you're going to find above 4 dimension. This might be surprising, and it was surprising for me. So at least for me. And then I think there's more work to do to provide an exact connection with spinning point particles. Above 4 dimensions, especially. Also in 4, I would say, because the corresponding is proven for spinless black hole, and for spinning ones, there's more subtleties because the spin has some kind of structure, right? So you're doing some expansion here, So I won't comment much more about that. So the question we ask, Macroreto, Vittorio, De Duca, and Doan Akpinal, is that what is a self-expansion for spinning particles? So we generalize this work that was done as all these people here, okay? So the idea is to use the model I was telling you before, the supersymmetric model, up to spin square. This is in the second order form, right? It's the same equivalent as before. You can use first order, second order. So you have 1x dot p mu, or the other form. You can write in this form. So you just have the normal spinless bit. So then you have this Grassmann part, that the just kinetic term, and then you have this Riemann curvature up to spin square. Of course, you need to add higher order terms beyond spin square. And then the idea is that you just expand around the background solution, okay? The story is interesting because the spin carries a mass, okay? So the spin isn't just a parameter that's sitting there doing nothing, but it's proportional to the mass of the black hole. So if you do an expansion in the mass ratio, that's also important. And so what happens is that because the spin is proportional to the mass, the light body effects, the spin light body effects are suppressed, heavy suppressed, so for each power of n. And instead the heavy body are enhanced. So now you rediscover something that's well known to people doing self-force or gravitational backward perturbation theory, which is, the first order in self-force is geodesic in Kerr, and not geodesic in Schwarzschild. Sorry, not the spinning body in Kerr. So that's the reason. So so anyway, so you can do some power counting, expand these actions. So you have to expand all these degrees of freedom quite carefully. So once you do organize the equation of motion, what you find is indeed like the first order term just reproduce like spinless geodesic in Kerr, and the first order, the 1SF action. So 1SF, I mean, I pick up contribution in this epsilon SF to some power, the first order power beyond the leading, okay? So the 0 SF is actually proportional to epsilon. SF is because the product of these two things is just ml, right? So the mass of the light body. So the geodesic one is just proportional to the mass light body, so it becomes proportional to 1 power. So this one is proportional to 2 powers. Something very interesting that, because of what I said, that the heavy black hole sources the metric. So actually the Ricci curvature and Ricci scalar are not 0, are delta functions. So this is very important. So usually people that solve the equation put things to 0, but you have that proportional delta function, you have to keep them, otherwise you get the wrong answer. So you can expand the GR action, not particularly illuminating. You might have seen this because it's the same in ADS or DS if you try to do 2-point functions like on a background, then you start to have terms like this because this is the just quadratic in the delta, so that's what you get in the same form. And this is what defines, for example, gravito propagator, right? In all these backgrounds. Okay. So what you can do, you can follow what has been done also in the spinless case. And even though the problem was originally 2 bodies and interacting with gravity, if you do power counting like in the mass ratio, what you discover is that you can do something very, very interesting, which is integrate out the heavy degrees of freedom. Remember, we are in a classical theory, so integrating out like here really means solving the equation of motion, because we are in a classical approximation, or semi-classical. And so basically you can integrate out both like the fluctuation of the heavy body and also like the fluctuation of the Grassmann variables associated to the spin. What you find at the end, even though you started with just the light body action, gravity, and the heavy body one, you end up just with the light body plus the gravity one, and plus a recoil term. So this is a non-local term, basically encodes like the recoil of the heavy black hole, right? So you can think the geodesic, the heavy black hole stays in the center, it doesn't move, okay? But if you go to the next order, because there is a radiation, then you get a kick. And the kick is this term, okay? So this is something pretty important that was done here for the spinless case, will extend to the spinning one, and it's very systematic, so it can be done in any self-force order. Special or complicated doesn't matter, right? So there are spin connections, there are curvature term, and it's also non-local. So this derivative of the -1 just means an integral, right? So it's compound notation, but it's nothing fancy, just a way to remember that if you go to frequency space, you have 1 over the propagator, 1 over all frequency. So it's easier to keep it like that. Okay, so once you get to the interesting physics, right? Waveforms and metrics, okay? Then you need to solve so I'm working at this 1SF order. So you find the equation of motion just by variation of the action. And what you find is this kind of equation, which might be familiar or not, but basically, if you forget this term and you do a projection, it becomes, Reg-Wheeler or Zerilli equation, if you do some mode decomposition. But this is the covariant version of it, okay? So in our case, what we found is that there is additional contact terms, this delta function floating around, and they are due to these recoil effects, okay? And the fact that basically, as I said, like Ricci scalar and curvature, like Ricci tensor, like they are not vanishing, but they are delta functions. Because our vector is not a vacuum solution, And so you might wonder, okay, but you never recovered the usual black hole perturbation theory, right? So this is very important. So and the point, this is something very interesting that I was puzzled for a while, but I think I finally understood like last year at some point that you can use some residual gauge freedom to actually, for the homogeneous solution, to actually move like the center of mass and the mass and the angular momentum to be, and these are the L equals 0, 1 mode. And so in this case, you choose coordinates that are adapted to the primary black hole, and you get rid of the contact term in this way. But yeah.
But would this mean that the recoil you have is gauge? And not...
Yes.
Ah, okay.
Yes. Yeah.
And it's gauge only from the non-static modes.
Exactly. Yeah.
Makes sense.
Yeah.
But so it's not what you said in words before, or because I mean you have a real recoil, right?
Well, you can choose coordinates in your space-time. You know, you have like, in particular in GR, right? So I mean, and this is a gauge transformation. So.
But this is because you are 1SF.
Yeah, you want to.
If you are 2SF,
then it's more complicated.
the recoil will be physical.
Yeah. It's much more complicated to accept because there are mode mixings, and this is not as simple. But this is particularly interesting because, of course, that's the starting point of black hole perturbation theory, which is not this, which is what we get to solve for CFT. So, okay.
So sorry, the first equation in what gauge was that? Like
Just Lorentz gauge.
harmonic.
Yeah, Lorentz gauge, like, and yeah. So, okay, so this now makes contact with black hole perturbation theory in the way that you know and love. And in particular, I'm now relying on Carlos Stoll, which has done all the job of going from that equation, or at least the projective version, to the modes at infinity and the horizon. Okay, so thanks for saving a few slides. And what you get, like if you solve the equation, like we have discussed yesterday, so you decompose, use symmetry of the background right now. So you have get rid of these modes, use the fact that you have like spherical symmetry. You can do some mode decomposition, and in particular, these will give like some modes at infinity and the horizon. Okay, these things are based on, for example, Tukowski press formalism. That's very old, but now it's been put like in a better, I would say, fashion, in particular for the calculation. In any case, so you get like explicit expression of the energy flux. So this is the energy emitted at infinity. Okay, but in time, so E dot in some sense. And the angular momentum, which are in terms of this, either the infinity or the horizon, right? These modes that Carlo derived yesterday. So they are exactly the same, I think, at least proportional. So then basically you see that the equations are very similar. So as was pointed out yesterday, like you have the infinity or the horizon on both sides, they look structurally very similar. And it's something very encouraging, if you want to make connection with calculation, particularly to absorption, that these things look so similar to each other. And this is something that I find quite interesting. So to get the full energy and momentum loss, you have to integrate over the orbit, right? Because now you have the differential ones. So these expressions are also valid, for bound orbits if you plug in the right trajectory. Now here I'm choosing scattering orbits, okay? So I choose this contour again, like integration from the turning point infinity and back, okay? And so, okay, they should be both energy here, because it's the energy of the horizon. Anyway, the point is that, like, here, this R dot, right, is a similar structure to what you saw in the deflection angle, right? Remember the calculation of deflection angle? I was saying you do some kind of expansion, singular expansion of the integral around like this particular solution, which is R dot equals 0. So you can do the same expansion here, okay? It's only at this point, right? So only we integrate over the orbit. It's a full contribution. This what says that the critical zoom wheel orbit I was showing before is what dominates the emission of radiation, okay? And it gives again a divergence, okay? And this is something very important because we start to talk about things that are physical, right? So we start to talk about things that have impact on gravitational wave modeling because now we're talking about the energy emitted and the angular momentum emitted. So the important part, so this technology also can be applied for bound orbits, although I won't talk much about it.
So Riccardo, just to understand, so in your Z, capital Z, you still haven't integrated on the particle trajectories time, right? So
No,
okay.
yeah.
Just the difference between.
That's the difference between, yeah.
So this formula for me would be already the total. I mean, the right hand side of this formula would be.
I think you have passed the integral inside, redefine your Z. Yeah. It's just that to get to this point is a bit long, as we see yesterday, because you have to get to the radial, the radial equation, and then to kind of define things. Sorry about these issues. Yeah, it's loading. So anyway, thanks for the comment. And then I want to say, exactly. So this applies also for bound orbits. And the point is that because this is still inside the integral, even if you integrate between the turning point, the radial motion for an ellipse is still inside. You can still apply this technology as I show in the plot of the parameter space, and do it as well. So what do we get out of this? So what's the outcome? So in this recent work, so this is with Lior Barak, Benjamin Litter, Oliver Long, and Niels Barbuto. So we study this in detail, and we obtain analytical expression for the expansion of the energy loss, both at the horizon and infinity, right? Applies to both cases. The structure is similar. And it also applies to angular momentum because unstable circular orbits are special because the symmetry, the radiation of angular momentum is related to the radiation of energy. Okay, two things are connected up to a frequency factor. What you find the same log as I was telling you about before, with a different prefactor, and the prefactor is actually the differential energy flux for the circular orbit, which makes sense. So it's the average. Is the average flux, okay, dE over dt, okay, evaluated on the critical orbit. And this is something that people study for a long time with the MST formalism. It's been one of the first things that have been done, for example, by Fujita, and in the PN expansion. Anyway, so it's it generalized. I mean, this formula, the divergence was known, but the prefactor was not known. So that's what we computed. And the interesting thing is that we can actually apply to actually improve perturbation theory. So now it goes into the spirit of things like resurgence and other things. So finally, we get a control of analytic structure in very strong field. So a very hard piece of the calculation. So we can basically use the known weak field series that we have computed, okay, up to some point, which is not converging very well normally, but then we add this log term, okay, which is done basically doing the job of reproducing the strong field, and of course you have to subtract what is common, right? And to subtract what is common, you just expand. This is for the post-Minkowski expansion. So the post-Minkowski expansion is an expansion in 1 over L, right? Because it's an expansion as we have yesterday, Gm over B, but B is related to the angular momentum. And so in expansion, also over 1 over the angular momentum. Okay, so it's a weak field, a large angular momentum expansion. So you want to subtract, if you do, if you have a weak field series up to a certain n order, you have to subtract up to n order in the expansion of the log. Okay, and this constitutes a uniform approximant of the solution. And we also include the PN expansion, so you have to do some additional work. Because this is easy because you see this prefactor here is this prefactor here, which is, for example, as I was saying, just the flux evaluated on this unstable circular orbit, but that has its own expansion in PN. Okay, so in PN it doesn't expand in PN because it doesn't have angular momentum because it's a circular orbit, but it expands in PN. So if you expand in velocity, you get some term. So if you want to actually combine all the perturbative schemes so post-Newtonian, post-Minkowski, and stuff, you have to also expand that. So you also have to expand this piece and all that consistently. Okay, so now you say, okay, what do you get, right? So we're getting the point that I say what we get. You can see the plot, well, okay, more or less. So what we get, we take all the state-of-art data from all the different communities, okay? So the 5 p.m. 1SF data, that's this famous nature paper, like in the weak field scattering by Humboldt group with Plefka, Mogu, Jakobsen, Sauer, Nega, and Uzovic and Dresse. And then we combine it with the 3 p.m. 1SF, so we ran a 1SF order. 3 p.m. 1SF calculation, which of course by Bini, Damour, Geralico, that's been done like quite recently. And then we combine it also with the strong field data. So we take all the analytic data in the same formula, and we combine it with numeric. So we check with the numerics. And what we find is that we had a very remarkable agreement, okay? Of course, you get agreement at the endpoints because where you're far. So this is like the distance, okay, from the black hole. So when you are far away, it's weak field. So of course you recover what you know, but you just get it numerically. You can check that the dots are equivalent to this. But you can also agreement in the strong field, where you are very close now to this separatrix orbit. So you get both the best of both worlds. Of course, the problem is an intermediate regime, okay? But I think it's still doing pretty good, and there might be also alternative resummation methods. We know that the type of resummation methods can vary, and there might be other ways to combine this data that can also give further improvements. For example, people in EOP use PADE or other kind of techniques. I'm not going to go into that. But the interesting point is that the improved accuracy is in the entire parameter space, right? So from weak field to strong field. So we have both things because we have controlled the boundaries. And the also nice thing, you can see these lines here of the error is the error compared to numerics. So it's only when you combine all of them together that you get the most precise, accurate result. So if you combine only PN data with the strong field, the result is up here, okay? So this is the lower the better, okay? If you combine only the PM data, you get up to here, but if you combine all of them, then it gets better. Also in the weak field. And this is, something that I find quite interesting because then it means combining data from one community just gets better. And this is something that I think it's for pursuing in the future as well. So I'll just very quickly, yesterday Carlo talked about the energy loss that was computed by Goldberger, Rostein, and then I think Jones and Roof, and then confirmed again by Carlo Rodolfo and the others. So you can combine the state-of-art data for the energy loss at the horizon, because the calculation is exactly similar, remember the story, the energy flux. With again analytic control in the strong field. This of course we have less analytic control because we have only 1 point essentially, right, analytically. So what we have done is that we have also used some accurate fit that Niels Barburton has done at 8 p.m. and 9 p.m. You can do it from, basically you look at the scaling, you subtract the leading term, and you look at the sub-leading scaling in 1 over the angular magnitude to some power. So once you do this, you get a better agreement, which is just saying basically we need more analytic results. Basically that's the punchline of this calculation. It's not as good as the other resummation, but it's something that we want to look forward in the future to put together these techniques.
I guess it's also saying that the leading PM result is correct.
It is also saying that the leading PM result is correct, yes. Okay, so I'll conclude. I'll say promising application of particle physics tool for the binary dynamics in general relativity. I think this is relatively new. I was trying to emphasize this point. So these ideas have worth exploring in the future. I think there are prospects of combining analytical and also numerical solutions of Einstein equation. People have worked very hard in the past, I would say even 70 years, trying to solve Einstein equation. But perhaps the idea here is that we don't do it alone as a community, but we do all together to kind of achieve the best accuracy. And I think this is particularly important for Lisa wavefront modeling, which I said cannot be tackled with numerical relativity tools. I think it's important from the theoretical side to study the phase space of the dynamics, right? In particular, to get application of symmetries or exact or approximate symmetries. So I talked about the radial action when the problem is integrable. I haven't talked about there's some new methods to extract observables which is based on brackets. And also this one meshed very well with this idea that I was talking about before. You can also think about relation to bound, scattering to bound. And again, like the methods I was describing are, thinking about energy and angular momentum as parameters in the space are the ones that are useful to try to understand like this relation between scattering bounds and of course critical orbits that I talk about. I'll also leave with some open questions. So since I could also talk about holography, and I think like maybe there is some prospect to actually think more about holography. And possibly, like, also in particular, I like the non-perturbative aspects of it, right? So we do holography also because we're trying to understand something more non-perturbative. And of course, the other thing, as I was saying before, is that it puts together QFT and gravity, right? In the same kind of program. And also, I think something also interesting, of course, I talked about integrability for the probe limit, but actually you can expand and I've also studied recently, like trying to think more about integrability beyond the probe limit, classically. I think that's also an important point. Yeah, thank you very much.
Thanks, Riccardo, for the talk and for staying perfectly on time. So,
that's right. Yeah.
questions? Please.
So, can you comment maybe on the high velocity or high energy limit of your summation?
Yeah. So, I think I didn't say, these velocities are 0.35, which is, velocities 1 will be ultra-relativistic. So this is still quite small. You can see that, well, of course, something you don't want to do is including PN data if you think a very high velocity, right? That would be not the right thing to do. Because if you're expanding slow velocity and then you want to do high velocity, it clearly is not a good idea. PM is a very good idea to keep it, but also we want to try to think more about expansions directly in the ultra-relativistic regime. So the leading order, if two black holes are very highly boosted, they become shock waves. And then basically this means that you do some perturbation around shock wave solutions in GR. And I think, so when we look at the high velocity, we saw, for example, we look at 0.7, and we saw that it's significantly worse. So I think like even just, so that's definitely something that we want to do for the future, try to think more about other expansion. So I talked about, the cube. So you might want to think about, essentially some other slicing of this in the high energy regime, essentially, just high energy ultra-relativistic regime. But it's very open problem. Yeah.
Thank you.
So the
Sorry, Eric,
no.
Fabio, maybe?
Okay. Maybe a technical question related to what you were mentioning about the dimensional regularization.
Yeah.
So what happens is one of the things that happen in high dimension is the multipolar structure of becomes richer. Does this play any role in this analysis?
Well, I mean, yes, because if you use the method diesel spinning sulfur CFT, of course, the less complicated this object is. So basically, we just want the generalization of Kerr metric above 4 dimension, which satisfies some equal motion with some couplings. So maybe I do expect that's why I was telling you that maybe it's important to push more on what you found on this minimal coupling.
The extra multiples probably they vanish if one of the two angular momentum is 0. So probably
but also really yes.
To one of the, there's only one if only one angular momentum is still known.
That, but also like this very simple minimal coupling thing.
Okay. But you still have
it's
not even clear what this depends on.
So as I said, there's more work to do, and this afternoon we'll hear.
Well,
maybe Rodolfo.
No, I just a quick question on the comment that you had before of adding an extra slice of information for the high energy limit. Do you have in mind to do some self-force around the shockwave background or things like that? Is this have this been tried or
someone else is doing it? I was doing it as well, but they are too fast. And their paper will appear in a week or two. So
okay, so
that's kind of the short answer. So I was trying to do it. I mean, it works.
And the idea is to study scattering angle and the waveform in this kind of self-forced based on shock wave? Or?
I guess the idea is to keep not expanding PM any self force. So try to keep like the full self force object and try to use, for example, the symmetry of the shockwave background to simplify gravitopropagator and other objects, and then use that to kind of get like at least some leading order contribution that's why to all self force order. So in such way you can slice in other way the cube. So
yeah, Alba had
Yeah, it was just a silly question. So what do you mean by the simplest one?
Oh yeah. So basically, in GR, like I mean, okay, there are two definitions of simplest. So if you talk to a GR person, we talk about Noether theorem and things like the fact that and the fact that you can basically just given the mass and the spin, you can identify a Kerr black hole in 4 dimensions. That's true in 4 dimensions. If you do above 4 dimensions, interesting, like there are infinitely many deformations. And this deformation can be characterized by some particular multipolar structure that Fabio was mentioning. Or if you think about the point particle perspective, it's some additional couplings. So there are more couplings. So you have an action with an EFT. And so say I want to reconstruct this matrix. So it means I take some point particle with some coupling, and then I compute an expectation value of the metric. To get, we don't understand yet what is the simplest one that arises in doing this procedure. So you're taking the simplest coupling and construct the full metric. So because when you interpolate above 4 dimensions, basically you open the door to having like I think stress tensor multiples, right? That's what you have. So you don't have only monopole and dipole contributions that are mass and spin, but you can have like contribution to the spatial components of the stress tensor, and these are new things. So depending on, you basically want like the simplest possible solution that interpolates to carry 4 dimension and retains simplicity in higher dimension.
And in this consideration, and this like way of saying simplest, there is no consideration about stability or instability.
Crucially not, because I think that it might be even some spinning naked singularity. It doesn't matter as long as it interpolates to Kerr. Doesn't matter because the procedure just goes through. If you choose the correct couplings, the fact that you have like some anything that looks like a point particle in 9 dimension, that even if he has some naked singularity, it's fine. It just needs to interpolate to Kerr and be the simplest. So I don't know what the solution will be because it hasn't been found. So Fabio has a paper where he computes up to I think g to the cube by doing calculations, with Feynman integrals, but it hasn't been done to all orders. So it's a completely open problem. And it is very interesting because it connects like the simplicity and a kind of effective field theory perspective of point particle physics with the simplicity of the GR perspective of the Noether theorem. So yeah. Thanks for the question.
further question.
Since I asked Carlo yesterday and he pointed at you, can you comment more on the scatter to bound map? Is there
usually, if you have seen previous talks, I usually give a talk about scattering to Baum, and not today, essentially, just because I thought it was a bit. So, where do I start? So, okay. So basically, the current status is that if you were in classical electrodynamics, when there is no hereditary effects, so things, basically. I mean, what it means that it's a linear theory. It's a linear theory. Then you can formulate in classical electrodynamics exact scatter to Baum maps, which maps like the variation of, for example, the angle here. So let me go back. Yeah. So here you can go. You can do this instead of integrating from over to infinity. You just over a period of the orbit. Okay. So you can do this and find exact correspondence. It is classical electrodynamics. In gravity, it's more interesting, right? Because it's nonlinear. So nonlinearities, so the presence of a trigraviton coupling means that essentially, eventually, and this is pretty clear when you solve, for example, the MST solution, you get hereditary effects. So effects that depend on the boundary conditions very heavily, because they depend on the entire past history. So if you have a causal cone, they depend on the entire past history. These effects currently they break the scattering to bound maps. But that doesn't mean that the particle physics tool cannot be applied to bound, because basically I think what's happening is that it's just a change of the boundary condition, which means change of boundary condition of how you integrate things. But the internal dynamics, like the dynamics of the equation, is the same. You can think about it this way, like if you take an Hamiltonian, right? The Hamiltonian applies both scattering to bound orbits, and the only point where bound come into play is when you put boundary conditions. You say, oh, I start with the scattering configuration, I evolve it, or I start with the bound configuration, I evolve it. But the Hamiltonian is the same. So for the same reason, you can translate this into some precise statement about how you organize this function.
So you will have, in your first slide, in the action, you will have to include a specific boundary term accounting for this.
Yeah, so basically, actually, the paper I wrote 2 weeks ago, that is on the archive, we try to do exactly something similar to this. But it goes, it's a bit refined, and it's for a scalar model. Eva, look, and if you want, can discuss. But we try to do this, so basically you can, because this is scattering, integrate up to -3 to +3, you can try to integrate over a period of the orbit. You have to be careful because there's lots of things about bound perturbation theory. Because you can have secular effects that break down, so it's very famous, like in very application of physics. And also, you be careful because usually actually orbits in Schwarzschild and also relativistic Coulomb are not exactly periodic, they are quasi-periodic, and it means that there is no zero precession of the orbit. So it's not exactly periodic. So you need to introduce some Alice function, which is called adiabatic expansion, which is all people use in the cell force formulation. So there is a whole structure.
And when people say it's related to an analytic continuation,
yeah, that I can write on the board, I think, if I remember the sign. So for example, the radial action for bound orbit, I think when it works, the analytic continuation, okay, so excluding the hereditary effects. So I discussed the one for scattering, right? So I think it's something like this, E and L, you can use J. L plus, I think, E minus L. Yeah, something like that. Let me see, sorry. Okay, so there is some equation. So analytic continuation in the sense that you take the energy, so this is, you start with energy that are above the mass, because that's what is being scattering, and then you go below this, and then basically you can use this formula, where here you flip the value of the angular momentum and you can recover this. And these are these boundary to bound maps. Yeah, but basically it's not the end of the story, because as I said, like this hereditary effect breaks this, but you can, so once you have this object, then you can take derivative and compute observables like pre-astral class and things like that.
Okay, I think we can thank Riccardo again.